Hey guys, welcome to our YouTube channel for my traffic class CE375. And today this video we will continue working on time-space diagrams. In our class we have discussed how we do this on a freeway, and let's do it a little bit more complicated example when we have interrupted flows, specifically when we have a traffic signal. So I'm going to solve a question in this video and show you how we do it, how we develop the curve, and also how do we get lots of information out of this curve. So I'm going to read it first, and then let's start working on the curve uh, on a piece of paper. You have to draw it to scale. So this solving this question usually happens by to scale graph. So let's read it. So we have here a pack or a group of vehicles, and we define simulation of vehicles, in this case similar to water. So we assume that vehicles all drive at the same speed and they follow each other in terms of something like a fleet or a pack of vehicles driving after each other in a queue. So a group of vehicles were driving along an urban arterial with an average speed of 45 miles per hour. In this case, guys, we will need to change our units to be definitely in not in miles. We need to put it in some kind of something where we can put on a curve. So it's gonna be changing our miles per hour into feet per second. And to do this conversion, the 1.47 secret number that we use in all our transportation equations will be the one conversion factor that we use. I'm going to show you in a minute how you do that. So we have a number of vehicles driving with this speed. After, let's imagine that they started driving, and I'm going to tell you about the start and end. There's an assumption that we will do here. Show you what I mean in a second. So into 2,500 feet downstream, the first vehicle started to arrive at a signal that's going to be red, and then it started to wait for 20 seconds before the red turned into green, and then it started moving at the green light of 40 seconds. What do you mean by that? The green time is 40 seconds. So once it started green, there is a counter inside the signal controller for 40 seconds. So the first car arrived at another intersection signal 3,000 feet away, and it happened exactly after 50 seconds. And we're gonna model all these values in the curve in a second. And let's imagine that the cars drive all in some kind of a pack. So the last vehicles, and we do, if you remember, guys, when we do this time-space diagram, we model the first and the last car as an ease. We can do it for every single car, but here we want to figure out lots of stuff on the curve, so we usually do it for the first and the last car. So the last vehicle arrived exactly at the last second of green light. So what's the last second of green light? Remember this 40 seconds. And adjust its speed according to the whole fleet of cars. So the last car, once it arrived, this signal is going to start to adjust speed. And I'm going to talk about assuming acceleration and deceleration are neglected. In other words, we're going to assume like the cars directly go to their cruising speed. It's an assumption, but this assumption is valid because cars do a little bit of some delay in accelerating and slowing down. But once they reach a few seconds later, they all drive almost in the same speed, which is the speed of the road. And then we're gonna calculate some stuff. So before we calculate all this stuff, I'm gonna get back here. Let's create the curve. So let's start with this 45 miles per hour. So first thing in a calculator, 45 times 1.47. So our speed is 66.15 feet per second. This is the speed we'll be using. Okay, 66.15 feet per second. So let's get here. This was just a, let me just create here a, let's create a new whiteboard. I was just doing some tests here, guys. So that's a new whiteboard. So I'll try to be as to scale as possible. So when we draw a time-space diagram, it's an XY curve. So on the y-axis, this will be our distance. And on the x-axis, this will be the time. And you guys draw it to scale. I'm trying to put it on my computer, but it's not gonna be as we do it to scale. So this is time in seconds, and this will be our length in feet, and use whatever scale you like. Let me also, I like to do this a lot. Let's put a different color here. This will be our work when we have a roadway, so the cars will start driving. So this will be my roadway. And let's here put to scale, let's put here, let's get back here and figure out what are the numbers. So this is my time and space diagram. So a group of cars were driving along the urban arterial an average speed of 45 miles per hour. And then there is 25 feet downstream. The first vehicle arrived at a red signal intersection. So let's get back here. And let's, yo, that's great. Let's make it like this. Let's create a new whiteboard here. So again, let me do it. I am trying to make it as small as possible so I can fit everything I wanted. And for you guys, when you solve this kind of question, try to get this engineering scale drawing paper to solve any question. So again, this is my x-axis, and that's my y-axis. And now let's start drawing the time here, and that's my length or space. So let's start here saying this is 500, 1000, 1500, 2000, 2500. And let's draw it like this. This is my first intersection at 2500 feet away when the first car started moving. And again, we're gonna draw the first and the last car. So that was the first intersection where the first signal will happen. And when we draw this, since we're doing the time here, and there is a signal, signals deal with time. So it's a signal, space is the same, it's the same area, but time, when time changes, the signal changes from, let me put here colors. So we have here red, and then green. Should be here. See. So let's do it again. This is red. And then some green. So there's red and green, and figure out what is the time for red and green. So when we calculated the speed in feet per second, it was 65.15 feet per second. In other words, if we look out at every 100 seconds, so 1 second you're going to move 66 feet. So for 100 seconds you're going to move 66.15 feet. So we can do it either way. Or for 10 seconds we're going to move 661.5 feet. So I'm just trying to find the speed here. Notice something, guys. If this is length and this is time, then let me just put this in black. So if this is length and this is time, length divided by time gives you the speed. So the slope of this curve is always equal to speed. So if you want to now calculate the speed, let's say the time for every second. So here 10, 20, 30, and so on. and so on. So let's imagine that the first car will start from time 0 and distance 0, which is the point here. And this car is going to move in space and time, then it will have a slope. And the slope in the first car was 66.15 feet per second, or 661.5 feet per 10 seconds. So for 10 seconds, it's going to be about 661, so it's going to be somewhere here. Again, I moved here 10 seconds, so I'm going to move up here 661, and this will give me the slope of my first vehicle. And then let's talk about this neglected acceleration. I'm going to draw it on the side here. What happens actually is that the car will start from a speed of 0, and then it's going to start to accelerate. So it's going to be something actually like this. It's going to go like this and like that. It's going to be have some kind of acceleration. Also, when we slow down, you don't just directly go to 0 slope or 0 speed. It's going to be something like this. You're driving with a speed, and then you do it gradually till you stop. This is the actual car movement, or the car movement in space and time. But in our case, we're going to assume it's neglected, and the car will directly go from 0 to my speed. So it's going to be like this. So this is the first car. Let me do it again. So it's a straight line with a slope of 66.15, and that will be my first car. See how easy, guys, it is? So let's get back to the question here. So the first vehicle arrived at a red signal intersection, and it waited for 20 seconds. So we can directly translate this into our curve. So the first car, let me just draw it in a better way. So the first car here started moving straight. Let me do it again. So the first car here started going straight, and once it went to this intersection, it found a red light. How much time it waited? It waited for 20 seconds. So let's say here, this is my time. It's gonna count 10, 20, and then let's just erase this. Oopsie. Yeah, I think I can do this with my pen. So let me do that. Okay, so let's get back here. So that's my pen now. I will just go like this, and this is now. So let's do it in red. So that's my red pen. So now he hit the traffic. So it was red when he came, and it continued to be red for about 20 seconds. That's 10, and that's 10 seconds, and then it started then going green again. So this is the first car. The first car will arrive, wait a little bit for red, has to stop, and then it's gonna go ahead and move again to the next intersection. And let's see how much green you get. So, and then start moving at the green light of 40 seconds. So we have a green light that lasted for 40 seconds. So let's do this as well. So for the green light, we started now going 10, 20, 30, 40, and then it's going to hit the red light again. So this is how the signal works. Red, green, red, green. So that was the first car. Let's figure out what happens to the first car again after it moves. So 40 seconds and arrive at another signal 3,000 feet away after 500 seconds. It's going to be messy. I'm going to be probably need a longer paper. But what happens here is that after 3,000 feet. So here, this is 1,000, this is 1,000. Let's just extend my line here. So 3,000, 3,500, 4,000, 4,500, 5,000, 5,500, 6,000. And again, this is my length. And let's delete this part here. Okay, so let's count after 2,500, another 3,000, so it's 55,000. So what happens to my signal is the following. So we have another signal at 5,500 feet. So we have a second signal at 5,500 feet. And again, let's put a line like this that tells me where the other signal is. Okay, guys? Now, let's go ahead and let's first again talk about the first vehicle and arrived at another signal 3,000 feet away after 50 seconds. So let's now put this. So after 50 seconds, this started from here, and you're gonna do it much better than me, guys, since you do it by scale. So let's count 1, 2, 3, 4, 5. So the first car will arrive from here to there. And exactly, I just have to pass these two lines. And that will be the speed of my first car. Now let's do the last car. And again, a pack of cars, we always love to use it or introduce it as a pack. First car and the last car. And we do this simulation line of the first and the last. So let's read again how it's worked. So the last vehicle arrived exactly at the last second of the green light. So when you drive a car and your last car in the pack, and then just before it hits yellow, you are moving and you arrive there and adjust the speed according to the whole fleet of cars. So once it went, the cars changed speed as you noticed. Once it went to the second road, and the last car will adjust the speed. So assuming acceleration, deceleration are neglected, we need to calculate these six things. It's so easy, guys, once you get the idea. So let's do the last car. So last car, once it reached here, exactly here, at the last time of green, it will find it green and it will continue going. One thing you have to note, since the first car moved with this speed, guys, then the last car will move the same speed. So these two lines will be parallel. Again, speed is the slope of the line. So this is the last car. All you have to do is just go ahead and start drawing the car like this. Okay, guys. So this is how you do the car, and you do it with the same speed. But there is a problem here. What's that? So I'm going to do an undo here. Is that what happens is that now we have a new speed. Maybe it's faster, maybe it's slower. And this is the speed of the second road. And it backs up to the first road. Since the first car will start going with this speed, everybody will go the same speed. So we're going to do it backwards. What do you mean by backwards? You're going to go here, and we're going to assume that both cars will be having the same speed. So something like this. I'm going to do just a parallel line. And that will be the last car. Okay, guys. So, so this is what we call here a pack of vehicles. But there is a point here where the last car will start adjusting the speed based on the first car. How do we know it? We know it by this distance here. Again, here is this a distance? Here, any vertical line here is a distance. Any vertical line here is a distance, and we call this spacing. But not spacing between any consecutive vehicles, it's the spacing between the first car and the last car. So there's a point here where the slope for the last car will start changing. And given that this last car will arrive at the last second of the signal. So how you do it? Since this car will start changing its speed at this point here, you want the same spacing to happen here, which is S here. Let's call this S1. So that's my S1. I want it to same here. And then it will adjust now its slope to the first one here. And given something, see this car has been stopped, but the spacing should be the same because the spacing cannot change. So S here should be always the same. Again, guys, let me undo it again. I know you need a little bit of so the first car will drive with a speed, it will hit a red light, and it will go with another speed. He's not so lucky. The last car is lucky because once he starts reaching, he's gonna drive with a specific speed, and then this car will speed up or slow down on the second stretch of the road, and the last car will adjust at some point. It will adjust its speed to follow the first car to the second intersection. The spacing is the distance between the first and the last car. And this spacing should be the same based on the speed. And this spacing should be also the same for the first one here. So we will adjust the speed. So you're going to draw here two lines with the first speed, the first slope like this, and then the second speed, something like that. If you're able to draw these two lines, the first line of the first car and the second line for the last car, you can now be able to calculate everything you can on the curve. So let's now calculate the stuff, and the calculations should be based on a two-scale drawing. In my case, I didn't do scale on the screen, but hopefully you get an idea. Let's now calculate everything you want here. So number one, the time where the first vehicle arrived at the intersection. Well, we have already the first intersection. So we want to know when is the time. It's already calculated. So it's asking you, when is this time exactly? We calculated the slope. We can calculate it by just multiplying the speed. It was 45 miles per hour, 66.21 feet per second. You want to know when is the time where the first vehicle hit the first intersection. So that's answer of number one. You can do it to scale, or you can go ahead and say, okay, 2,500 vehicles, 2,500 feet with a speed of 66 feet per second. So what what second will I arrive? So it's the feet divided by speed. So it's 2,500 divided by 66. It's give you this how many seconds you will arrive exactly here. That's answer to the first question. Again, you can do it by analytical, but you can also do it graphically if you did it to scale. So that's the first thing. Second question. So we did this. The headway, and again, headway is the time difference between cars. If you are counting cars and you have a timer, it's the time difference between one car and the other. So the headway between the first and the last vehicle of this fleet of vehicles. So how you do this? Well, that's the time difference between the first and the last. This is when the first arrived, and this is when the last one arrived. So that is the number two, the headway. Again, this is when the first, let's imagine that you're sitting here and the first car arrived, and then the second, and then the third, and so on. The second arrived this time, third arrived, and then comes the last car, this car here, and it's gonna arrive on this time here. So here, this is the first, this is the last. So here the time, you can see now, once you draw the curve correctly, you can now calculate anything on the curve, and this is called the headway, or the time difference between the first and the last car on the road. So we did number two. What's the speed just downstream of the intersection? That's again so easy. You need just to calculate anything. So the speed, once it reaches the first intersection, it starts moving with a different speed to arrive here exactly at 50 seconds. So the speed here is the slope of that line here. How to calculate the slope? Just measure any distance, measure the y over x, or here the length over time. So your speed here equals L over T in feet second, and then you divide by 1.47 to calculate it in miles per hour. So again, it's the slope of the second line. Okay, so we calculate number one, number two, and number three. What's the spacing between the first and the last vehicle? We calculated the spacing, if you remember, guys, by graphically on the curve, or just by a graphical way. This is the spacing between the first and the last car. So here you just measure any distance here. That gives you exactly the spacing between the first and the last car. Should it be the same? It should be the same everywhere. And that is the distance spacing between the first and the last car. Okay. Approximately how many vehicles are in that fleet? So let's say that, let's just measure it. So let's say that the spacing here is 1, 2, 3, and let's say 400. So it's how many? 1,700 feet, approximately. In my case here, 1,700 feet. So I want to know how many vehicles, n number of vehicles in this fleet. How many vehicles? So I have to assume the following. What is the spacing between every two consecutive vehicles? Well, if it's so packed, this spacing will be around the average size of a vehicle. So I say here, assume appropriate spacing between every two consecutive vehicles. So you can say here, assume the spacing between every consecutive vehicle, let's say 40 or 35 feet. So in my case here, gonna get back to my curve here. If the spacing between the first and the last vehicle is, let's say, 1,700 feet, and I divide it by 35 feet, which is the spacing between every two vehicles, it will give me an approximate value of how many vehicles are packed in your fleet. In other words, let's say this is the whole number of vehicles, and they occupy a space of 1,700 feet. And the spacing between every two vehicles I assumed about 35 feet. So I go ahead and divide 1700, 1790, just to show you that the numbers here are approximate in my case, divided by 35. So I have 51 point something. So let's say I have in this pack of vehicles around 52, or n equals 52 vehicles. Okay, guys. So that's question number 5. If you want to adjust the traffic signal timing, what will be the values of something called offset and something called green time? And this is part of the signal design. Once we have now this kind of curve, we can go ahead and look here. Remember when I put here the green and red? I want to adjust so the first car and the last car, both of them, will find a green light. This is what we call here by adjusting the traffic signal timing. Well, so I will just put it like this. Let me figure out this. Yeah, this color should work. So I want, once this car arrives with the same speed, I want it to arrive and find a green light. So this is called the time where this car started moving from here and it arrived here. We call this offset. And let's just put this in this nice rainbow color here, or put it in dotted. And that's the first car. And the green timing now will also be adjusted. So when the last car will come with the same speed, it will also hit a green light. So this will be my offset. Let's say 10, 20, 30, 45 seconds. Let's say just 45 seconds, my offset. And the green time will be 10, 20, 30, 40, 50, 60 seconds of green time. So this is what we call here something called an offset and something called the green time to give the green. So now I was able to adjust the timing of the signal that will allow the car not to stop, so to reduce the delay of this fleet of vehicles. And this is one way how we do a design of a traffic signal. So by this, guys, I end this video. I just wanted to review with you guys a time-space diagram. I want you to start testing this, solving the same question. I'm gonna post this question on online on eCampus and also here on the video. So if you wanted to go ahead and start working and doing it to scale and bringing that in class to discuss together. Thank you guys and have a great day and wish you all a successful